We're going to be transporting ourselves to 1985 in this episode, so I suggest you listen to Everybody Wants to Rule the World by Tears for Fears, which comes from one of my favorite movies, Real Genius. If you used computers in the 80s, there was an awfully good chance that you used magazines like this, Commodore Microcomputers, The Best of 1985. This is one that I've had in my personal collection that I got from my brother for the past 31 years. So, these magazines always came with programs to type in, and they were full of these things. And you would have these listings that would take sometimes hours to type in, and if you were unlucky enough to not have a disk drive, you possibly had to type in every single time you wanted to run the program. But you would type these in, and you would see these lines of for loops and stuff and comments, and then you would get over here and you would have these data statements, and you would be typing in numbers and numbers and numbers and numbers and numbers for pages and pages. Sometimes I believe some of the ones that I typed in were probably 5 or 6 pages long, and oops, too bad if you got a number wrong somewhere in the middle of it and the program didn't run quite right when you started it. Now, as a kid, myself, in the 80s, I typed these numbers in having absolutely no idea what I was doing. But it's really not that hard to understand what these things are doing. So let's give it a look today and see what we can find. We know that the Commodore 64 has a CPU called the 6502. And we know that because of some manual that came with our computer, or maybe we had heard it in some magazine. But we don't really understand what the 6502 can do and what our options are for trying to program it. But at the very basic level, the CPU has to execute instructions to make the computer do things. And we saw how that works in our last episode, for example, sending a value to the video chip so that we can change the border color on the screen. So, referencing back to that example, we know that if we can store the value 53,280, that is the value 1, at the memory location 53280, then we can change the background color of the screen to white, the border color. So let's say, what exactly is this Poke 53280 from our last episode even doing? We know that what we want to do, in the most basic sense, is store the value 1 at memory location 53280. So if we know that our computer runs a 6502 and we happen to have a manual for it, we might start poking around in here to say, well, what can we do with this thing? So let's do a search for the word store. And we see here that there is a basic command built into the CPU that can store the accumulator. Now, we have no idea what an accumulator is, and we don't really know zero page, what is this, what are indirect, we don't care about these things at the moment, but we do notice this absolute. And this maybe is going to mean something to us because we know from our last episode that the value 53280 is equal to this hex value right here, D020. So we want to store the value 1 at the memory location D020. And we've even put this $sign in front of it so that it looks like what we see in the manual that we have available. So we see that this command to write to a memory location is called STA, store accumulator. And it is the value 8D, and hex represents this command, store accumulator. So we know the very first thing we're looking at doing is we want to give the CPU the command 8D. And now I'm going to have to jump a little ahead in my description here, because we don't really know yet how things are loaded into the processor. But what we have to do here is reverse the value of these two things. So we want to, we're calling the command 8D to store, and we want to store at the location 20D0. Unfortunately, we have to swap those around. Okay, but now we're left with, what do we want to store? We know that we want to store the value 1. And we know that we're doing something called store accumulator at 20D0. So what is the accumulator? Maybe we can find something to work with it. And if we look for accumulator, we're going to see all kinds of things that operate on the accumulator. It seems to be a rather important part of the CPU. No, we don't need to compare values. Ah, what is this? Load accumulator. So taking this load accumulator, that is the value we want to do a absolute load. No, we want to do an immediate load. This absolute load, notice this pound sign right here. This is telling us we want to store a specific value in our accumulator. So our next command that we're looking at is LDA, and we want to load the value 01. So we have this command that's saying store our accumulator at this memory location, and we have now our second command, which LDA is A9, and we want to load the accumulator with the value 01. So these are the two things that we need to do. And now we've worked our logic backward, so this actually needs to come up here. So to get the computer to load the value 1 into the accumulator, and then to store the value in the accumulator to memory location 53280, we need to give the CPU this series of commands. A9, 01, 8D, 20, D0. And in a later episode, I'll go into some more of the details for how we knew that we need to swap this 20 and D0. So now we know we need to store these, we need to give the computer this set of commands. And we need to convert this from hexadecimal to decimal. The second digit here, so this A, is worth 16 times its value. So this is worth 1 times 9, and this one is worth 16 times A. And this works similarly to how it would if you are in decimal, and you've got the value 20, and we're talking in decimal now. This is worth 1 times 0, and this digit is worth 2 times 10. In hexadecimal, we have 16 possible values, not 10. So we've got this. So this is 9 plus And we know that A is 10, so this is 160. And so that makes our first digit, the decimal value, 169. And our second digit is 1. That one's easy to figure out. So D is the value 13. So we have 13 plus 16 times 8, which is 128. So 128 plus 13. And this looks all correct. So this is our final set of commands. And I'll write it down here for clarity. Now we need to figure out how we can send this to the CPU. And we have some clues waiting for us back in our trusty Commodore magazine. We see two things that give us clues here. We see a for loop with a read statement, which is maybe not fully visible to you, and a poke, and then we see finally a syscall. And these are the things that we're going to look at: our for, our read, our poke, and our sys. So we're going to start by creating a basic line that is a data statement that has these values we know we care about. So we've transcribed them here. And now we can list the program here. What we need to do is read each of these values. And we know that we have 5 values to read. It's not terribly complicated. So what we're going to do, and this is again something that I'll get into in a later episode for exactly how, but let's start. We're going to say that we're just going to copy from the example that we were looking at in our magazine, because this is how we would have learned if we were programming back in the 80s and didn't have the internet yet. So we are going to start at this random memory location from our perspective, 51712, and we're going to read 5 values. So that's going to put us at 51716. And then we are going to read into the value y, into the variable y. And then we're going to poke, just like we did in our earlier example in the last episode of saying poke 53280, comma 1, we're going to poke z, comma y. And then we're going to do our next loop iteration. So that will have loaded the 5 values that we care about into memory starting at location 51712. So then we are going to use this statement called sys. And again, we're pretty much doing this just because we've been reading our basic examples in our Commodore magazines. And we're going to call sys 51712. And ultimately what we're doing here is we're telling the basic interpreter that we want to load, let's list this back out, we're going to create a for loop that reads each of these numbers from our data, writes it into the memory location starting at 51712, and then we are going to jump into 51712, and we're going to see what happens. Now what happened? We just saw a quick flicker of light. We just saw a quick flicker of white, and then it all went away. but our program is still here. Now the problem is we created this little routine and we told the computer that we wanted to jump into it with our 51712, and then what happened? And then it just kept going. There's nothing to tell it to stop after it got to this fifth one. So it just executed whatever random values were in memory and then eventually got dumped back to the basic interpreter, which reset the screen values for us. So we need to tell it somehow that we're done executing and we want to return back to the basic interpreter. Let's see if there's something that maybe looks like return. How do we return? Wraparound, logic, load. Let's see. RTI, return from interrupt, no. Return from subroutine. So we create a subroutine, we call it with sys, and we want to return back from it. And we see this is the value 60. So 60 in hex is 6 times 16, which would be 96. So let's put our return statement here. Then we need to increment our loop. Need to hit enter on each of these lines and list, and now we have added our 96 and we've expanded our for loop, and we run, and ta-da, the background is white. And so let's put the background back to some other color, the border that is. Now it's brown. And now our machine language subroutine that we created here on 40 and loaded into memory is still, in fact, still in memory. So we can just call 51712 whenever we want to and execute our handy machine language subroutine that we just wrote. And in future episodes, we will go into more detail as to what we can really make this do and how we can take advantage of the CPU. Thanks for watching. Be sure to check out my other channels, subscribe, and leave a comment below.